There is an increasing scientific and legislative interest in fairness, explainability, security, and privacy. At the same time, we are also noticing research and commercial investment in accessibility. But can we explore and enhance privacy for users with special needs? Hello, everyone. I'm Ghosh, and today I'm going to present our work, PrivPAS, a real-time privacy-preserving AI system and applied ethics. This work has been undertaken by my colleagues and me at Samsung R&D Bangalore in India. To set some context, if we look at the current market scenario, more than 1 billion people are currently in need of assistive technology. And if we go by the predictions, by 2024, this market is going to exceed beyond 26 billion. Recently, this has led to this traction where academic institutions as well as commercial tech giants are investing to understand whether AI can be used to solve the problem of accessibility or to mitigate the challenges that people with special needs face. So the problem statement that we define for our current work is that given a single camera viewfinder image frame, can we detect and localize whether a person with disability is present in that photo? Here, a question arises that how do we define or whom do we define to be part of this group? Secondly, we want to understand whether this person of interest is aware of an ongoing photography. That is this photograph that we are passing as an input. Here the question is, what is the metric that we use for proxy for awareness, or how do we define awareness for the lastly, we want to do this in real time on edge devices. One possible use case could be deployment on smartphone camera application. If we look at the current scenario, 3 billion images are approximately shared across social media daily. And the evolution of smartphone cameras has led to such a photography explosion that almost 85% of new pictures are actually coming from smartphones, which we see on social media. At the same time, people with disabilities actually comprise around 15%, which is a significant part of the world population. And yet there is a significant lack of focused attempt to mitigate their privacy concerns. So in this work, we want to provide an on-device solution which can do a real-time detection of human subjects with specific disabilities. And we want to do it in private while training on privacy-preserving face-obfuscated images. Our goal is to encourage digital photographers so that they can have an ethical choice, or they are aware, sensitized of making an ethical choice of seeking consent before photographing unaware subjects who may be having a disability and may have special concerns or reservations against photography. This can probably also enable automated systems who can probably selectively announce recording status, or probably anonymize people with disability, or give any kind of other preferential treatment to those who are in need of it. While we may note that while mitigating the possibility of a malicious actor to bypass the ethical queue is beyond the scope of our work, but it does not add any additional risk to the status quo. So our proposal of PrivPAS is that it is an on-device, real-time privacy-preserving system. And we do a data curation for this task. As we will note in the later slides, that data is a real concern when it comes to this particular problem. And we annotate the data and then produce a face-obfuscated versions of this data curation for this data set. Next, we come to object detection. So we want to identify if a person with disability is present in the image. So we perform object detection for accessibility markers. So, next, we perform an eye gaze detection, which is something that we use to determine whether the person may be aware or not of such an ongoing photography. And this entire process has all the design decisions have been taken in a way so that on-device inferencing can be done, so that it should be lightweight, efficient, and should be entirely capable of running on edge devices or low resource constrained devices. If we look at the related work, we'll just discuss a few of these such works. So one of them is the deep detection of people in their mobility aids. We'll come to this mobility aids later. Here in this in this paper, what the authors have proposed is that their pipeline can estimate the position and velocity of people, of actually all the people who are part of image frame, and categorizes them according to if they are using any kind of mobility aids or not. However, if we note that this pipeline does not work on privacy preserved data, so if we remove the faces or if we obfuscate the faces, this model does not discuss or explore whether we can whether such a pipeline would be efficient at the same time. At the same time, eye gaze tracking or any kind of awareness is not determined. So if there is a human being who is looking even away from the camera, totally facing facing his back, even that you would be considered as a single subject. Next, we discuss another work which has been a very recent paper in 2021. Here, they are actually going about blurring faces as well as swapping faces, and they're seeing that even after doing such kind of privacy preserving actions, object detection performance is actually getting retained. So this is actually one of the motivation why we are taking up this task, and we are trying to see how if we remove the face information and if we preserve the privacy, how we can perform the same task at the same time. Lastly, if we look at some of the eye gaze tracking, we'll explore some in the later slides. Here, all the current work that usually determines with eye gaze tracking, they perform eye segmentation, gaze recognition, and even test varying lighting conditions, but they mostly have different use cases altogether rather than what we are targeting. Most importantly, none of these talk about any kind of accessibility markers detection, and definitely are not feasible for on-device processing sheerly because of their huge model size. So the dataset curation that we perform for this PrivPAS, it has been curated from Flickr open source. We have curated images where people with crutches, people with wheelchairs, and structurally impairment are present, and then they have been annotated by multiple users. And after cross-validation, we have annotated using this Microsoft visual object tagging tool. And after cross-validation, we have determined the boundary boxes for every individual with disability that are present in the image. We are also locating which of the accessibility markers are actually present. Let's say wheelchair, structural impairment, and crutches. These are the three classes that we primarily focus on. And also each image, wherever a individual with disability is present, we also annotate a binary label, whether it is sensitive or not. So if more than a 2/3 of majority of our annotators are actually of the opinion that this image is sensitive, or in the sense that the person is not aware of the photography, then we mark it as a sensitive image or unaware. If we look at the data set, this is we have around 905 images after cleaning or after ruling out the images where the annotators were not unanimous in their decisions. So now, to increase the size of our data set, we perform some augmentation techniques. We perform rotation, scaling, changing the brightness, translation of the images, and flipping. So we use IMG-aug library, which is actually taking into account the bounding boxes, and in the augmented images, these things are also preserved. So we also get the bounding boxes for the augmented images, even after doing this augmentation approaches. After augmentation, we actually come down to face anonymization. So once we have the images, so after augmentation, we had around 9,550 images, 10 times of what we started off with. And for all of these images, we perform face anonymization. So for doing this, what we are essentially doing is we are identifying, let's say there are M-face bounding boxes which on the image, a particular image. Then for each image, once we locate the bounding box, we are actually increasing the bounding box rectangle on all sides at the very beginning to make sure that the bounding box is covering everything like forehead and chin, which might have got missed by such determination of by such face detection. So for the face detection, we are using MLKit's face detection model, and therefore we are just enlarging this box so that the box covers entirely of the subject's face. And we use Gaussian blurring thereafter to using the OpenCV's library to anonymize the face. So it performs a kind of blurring, and the final resultant image, if we look at the example here, it preserves the essence of the image, it preserves everything else of the subject as well as the background, but it removes the facial, the features which can be used to identify that individual, like eyes, nose. These are some of the sample images in our data set. These have been annotated, as we discussed earlier, that these have annotations of the bounding boxes. What are the coordinates of the bounding boxes? Which kind of accessibility markers are we seeing in this particular image? So is it wheelchair? Is it a crutch? Is it a structural impairment? As well as we are also annotating like whether the particular person whom we have determined to be in need of to have disability, whether this individual is actually aware of the ongoing photography or not. Coming to our model for the accessibility markers detection. So in order to perform an object detection, we want to we want to do it in a most efficient way. So we choose YOLO V3, so that which the name says you only look once, so that essentially it takes multiple, it can detect multiple objects and their location just by processing one image. And that's why we go with YOLO V3. And secondly, our data set is not huge, so we decided to go ahead with transfer learning. We took YOLO V3's model and trained it on ImageNet 1000 data set. Basically, we took the pre-trained weights from that YOLO V3's that model. And after 51 epochs, for the first 51 epochs, we essentially trained it by freezing the weights of the original model. That helps to stabilize the loss. And thereafter, for the next 51 epochs, we unfroze the weights of the model and fine-tuned the model weights so that it can learn from our custom data set, which we have curated earlier. So in our data set, we use around 90% for our training, and we keep aside the 10% for later on validation. Before coming to the core architecture of the model that we are going to discuss, here are some of the variants that we actually explored while working on this problem. So the difference is primarily between whether we are using YOLO V3 or YOLO V3 Tiny. So the YOLO V3 Tiny version has a benefit that it has lesser model size, and it may help us to do an on-device deployment at a much more efficient way. Secondly, these models also differentiate between data augmentation, whether data augmentation has been done or not, basically whether they have been trained on data augmentation, data augmented path. And face anonymization is also a differentiating factor between these models. So if we look at the validation or MAP, which is the mean average precision, here, if we look at M1 and M2, let's take this example. Here, face anonymization is the difference between M1 and M2. And we see a validation that MAP is actually decreasing once we do the face anonymization. So, but this decrease is actually expected, because when we remove the facial features, it actually takes the essence that it is a human being, a part of the essence, because we are removing the face of that person. But yet we can observe that the loss is very less. Whatever drop is there, 89.46, 88.92. Similar drop is also observed in M3, M4, M5, M6, M7, M. However, if we check the big picture here, once we use YOLO V3's tiny versions, which is if we go by M5 to M7, M final. M final is what we are calling our M8 earlier version. So if we look at the values of validation MAP from M1 to M4 and M5 to M8, the values are actually higher for M1 for M4. However, if you look at, if we also take care of the size of how much size of the final model becomes, we see there is a huge drop from 60 to 8 MB. So we decide to go ahead with the final version as M8, although there is a slight drop from 89.58 to 89.52. Here we are doing face anonymization in this M final. The result is that our data set does not contain any kind of face information or identification of an individual, and yet it is able to perform to this level. So detailed architecture of the final model here, it consists of a feature extractor component made up of 6 blocks of 3x3 convolutional layers, and then we follow it up by max pooling. This is followed by skip connections inspired by ResNet, and finally, it consists of multi-scale feature detectors. So this multi-scale feature detector is used to ensure that small objects are not missed. Now we come to the next stage of our problem. Once we have identified the boundary boxes and we have identified the individual and person of interest, we want to understand whether the person is aware of the photography. For this, we proceed with eye gaze detection. If we look at the related work in eye gaze detection, there has been focus in public welfare, commercial drivers, and in smartphones recently. If we look at the public welfare cases, which are actually quite recent, traffic accident prediction, prevention, healthcare. So these are some of the things which are getting attention now. But commercial drivers like television and advertisement, these were has been getting attention for more than a decade now. And in fact, we can see in some cases that there have been this idea has been explored. If by looking at the image of a person who is sitting in front of a computer, by looking at them using a webcam, can we determine which portion of the screen is drawing their attention and whether we can monetize it? So that has been something which has been explored in literature previously as well. That it has a good commercial incentive. However, what our interest is not something that targets the user, but we want to explore whether if the user is actually trying to take a photograph of someone, of some person who has a disability and who has a special needs, whether we can provide a cue to the user that you should go ahead and seek consent. So even in smartphones, if we look at the recent usage, since we are also concerned about on-device deployment, in smartphones, there has been work regarding this for power optimization. If the user is not looking at the phone, let's dim the brightness. If the user is sort of making gestures using their eyes, whether we can do a kind of scrolling so the user don't have to touch their phone. But they all rely on a front camera case. So in case of front camera, the eyes are always pretty close to the camera and it occupies a significant portion in viewfinder. So this makes our key challenges as these are the two key challenges that we face in our problem. That detecting the gaze of eyes is difficult because a very less portion of the image is actually captured when in our use case, in the kind of use case that we are targeting here. And secondly, identifying the facial contours of just one person of interest is essential for our case. We don't want to do a facial contour identification of all the persons who are appearing in an image. Just we want to focus on those people who may have a disability. For this, what we are doing is we are first getting the bounding box coordinates, which is coming from our object detection model. And thereafter, we are obtaining a modified image, which is basically a cropped version, cropped by the bounding boxes. And then we use MLKit's face detection to derive select facial features and feature contours for those images. So these are some representative images. These are actually the output predictions as well as the we will see in the later slides. But these are some of the images how we are determining. Like the first image here is looking directly at the camera. We are clocking it as aware. The second image is, although the eyes are not that much open, yet we can determine that it is close to the camera. However, we can't determine whether the person is aware of the photography, so we label this one as not aware. So these are some of the examples. For eye gaze detection, our model is first taking facial features from the ML kit. We primarily focus on 4 of the inputs that we get from here, which is the rotational coordinate along y-axis, how much the user, which is like a proxy of how much the user is looking directly towards the camera or opposite towards the camera, or what's the angle. Secondly, we check the probability, whether their left and right eyes are open, so that we can take a mean of them, and the probability whether they are smiling. So this is one factor which we considered to take care of the fact of a candid photography, and which are understandable by any user who looks at the photograph, whether that person actually consented to that photograph or whether the person at least was aware of such photography being happening. So after taking these parameters, we compute a different parameter FRPOI, which we will discuss in the next slide, and we feed these inputs to a logistic regression model. Essentially, this logistic regression trains on annotated ground truth. It tries to learn weights for rotational part and for our inputs from the IE and for the smiling part, along with a constant bias. And this is the model that we then pass on to our on-device inference engine, which if in future any kind of image comes as an input, these values are extracted from that image. After basically, it's just a simple arithmetic of all this values getting multiplied by those weights, and then we compute our APOI. How we will compute, we'll see in this next slide. So we define a relative rotational factor for this person of interest, which is FRPOI. So this is the definition of that. In layman's term, we can think of it as how much the person is looking away from that from the camera. So FRPOI will be 0 if we are sure that the person is looking exactly towards the camera or within a very limited threshold. So for our experiments, we have this threshold determined as 10 degree. We set it at 10 degree or pi by 18. And this is what we compute to basically act as a proxy of how much the person is looking at the camera. There is a constant that we define here, which we have simplified so that it can be learned along with the constant part instead of adding it into the computation here. So when we compute the APOI, which is our awareness score, this is a function of this FRPOI and the mean of our eye similarity, our eye probability, and it also takes into account the smiling probability as determined by MLKit. So in our experimental settings, once we have trained this entire thing, and we set the decision boundary for APOI to 0. So anything negative is not aware, anything positive is aware. 0 is the decision boundary. After training that, these are the values that we have retrieved for WRWE and the other parameters. So interestingly, we may note that WR is negative here. This is actually expected because we are determining FRPOI as 0 if the person is looking directly at the camera. So it is essentially doing the opposite of checking it. Now in eye gaze detection, these are some of our observations once we tried to pass such representative images. So again, we return back to those representative images earlier, and these are the determination. So we see for these 4 images, we are at least able to determine whether they are aware or not aware. So yeah, as if it is negative, it means prediction is no. If it's positive, a prediction is yes. It's been computed from these values which are coming from MLKit. Now, to determine the performance, how good our original object detection model has been. So we explored the different variants of our model, M1 to M final. And if we remember that there is a difference that face anonymization has been done from M1 to 2, M3 to M4, then augmentation has been done between yeah, this is one of the special cases in M5 and M6. If we look here, they haven't been trained on augmented data, and we can see that structural impairment is actually at 0. So the reason is that this mean average precision is coming to 0. It's because we don't have much structural impaired image in our original data set to start with. So when we rule out the augmented data set, the model hasn't essentially seen much structural impaired data set. Is in data samples. So it fails to recognize the structural impairments without the data augmented data. So it also helps to convey that augmentation is helping in our case. For our computation, we use the intersection over union to measure this MAP. Lastly, we observe that for this M final, we have around 8.49 MP after quantization. That's the model size that we are getting. And on the validation set, we have 89.52% of MAP. Now, also to benchmark it with a public data set, we have used mobility data set, mobility aids data set, which we discussed in the first related work slide. Here, this dataset did not contain images of class structurally impaired class. So we perform analysis on the only two remaining classes, which our model was also trained on, which is wheelchair and crutches. And we observed that our model results in an MAP of 74.51%, and also a high average precision individually for both of these classes, if you look here. So the error in crutches category, it can be attributed to similar body posture and position as structural impairment, which our model has defined separately on. So essentially, our final MAP is 74.51 on this mobility aids dataset. We evaluate our eye gaze detection. We take the precision, recall, and F1 scores or around against 500 unseen images. We do it in two settings. One is without any kind of object detection. One is with object detection. So without object detection, it means that we don't know which individual we're concerned with. We are just doing a min scoring or average scoring. That is, we take an aggregate of all the individuals whose face is visible in that image. As expected, once we have done the object detection, we know which person we need to focus on. Our precision, recall, and F1 all rise up significantly. This is observation that naive aggregation won't be useful here, and we definitely need something like an object detection to complement this eye gaze detection system here. So to conclude, we faced a few challenges to start with. That is, the data set availability for such kind of for users with disability is really very sparse, and not much prior work has been done to which targets to protect their privacy. So we proposed this PrivPAS, which is lightweight. It has a real-time processing of images, and it is trained totally on a privacy-preserving data, which can be an example or a precedent for other such work, which can be trained probably on a privacy-preserving data set. We also curate and augment a custom accessibility data set, which has a 9,550 images after the augmentation. And our accessibility marker detection model is only around 8.49 MB, which is very efficient for a non-device deployment. It has an MAP of 89.52 on the validation set and 74.51 even on the mobility edge data set, which is available. Eye gaze detection F1 score independently is 0.731. So with that, I would like to thank you all for your time. And if you have any questions, we can like to take this now. Thank you.